Okay, so good afternoon to all and welcome to lecture number 17. Today we will start the block diagram reduction technique rules. Uh, so already we have started how to basically reduce the block diagram, complicated block diagram. We started introduction of that one, and today we will see the different rules which are used for reducing the complicated block diagram into a single or equivalent block diagram, and then how to find out the transfer function with the block diagram reduction technique. So that we are going to study in today's lecture. Okay, so you know that the control system characteristic equation, what is meant by characteristic equation, and so on. And here, the closed loop transfer function of a control system is given by CS by RS. So CS is the controlled output, RS is the reference input, which is equal to GS upon 1 plus GS HS, GS into HS. So this sign will be positive if there is a negative feedback, and this sign will be negative if there is a positive feedback. So if positive feedback is there, this will be GS upon 1 minus GS of GS HS. And if negative feedback is there, then this will be GS upon 1 plus GS HS. So it will be exactly opposite. This sign will be exactly opposite. And this denominator in the transfer function of this closed loop system is nothing but the characteristic equation. So the denominator of a closed loop transfer function determines the characteristic equation of the system. And if you equate that one equal to 0, okay, then we can find out the roots, and then from that roots also we can tell whether that system is stable or unstable. So the denominator of closed loop system is called as the characteristic equation, right? Now see that what is by canonical form of a feedback control system. Now see that this is a forward transfer function which is represented by G of S, and a feedback transfer function which is represented by H of S. Now why these two blocks are connected in feedback? So look at this one. Look at this one. Basically, this signal is flowing from left to right, and this signal is flowing from right to left. So that's why this is in feedback. Otherwise, if it would have been, suppose for example, this signal is from left to right, this signal is also from left to right, then these two blocks would have been parallel rather than in feedback. But here, this signal is having a direction from left to right, and this signal is having a direction from right to left. So these two blocks are connected in feedback loop. So R is the reference input, C is the controlled output, and B is the feedback signal. So this error will be the reference minus feedback. So error will be reference minus feedback, and then this is given as input to the forward transfer function. So Z is the direct transfer function, or it is also called as the forward transfer function, where H is nothing but the feedback transfer function, right? So this is nothing but the feedback transfer function, and this GH is nothing but the open loop or open loop transfer function. So if you take the product of G and H, then it is called as the open loop transfer function. And if you take the ratio of C by R, so output divided by reference input, or output divided by input, so that is nothing but the closed loop transfer function. So closed loop transfer function, or it is also called as the control ratio C by R, is given by G upon 1 minus Z plus 1 plus Z 1 plus or minus Z H. So as I said that if this feedback is negative, means this sign is negative, then it is called as the negative feedback. So if this negative feedback is there, then this denominator will be 1 plus GH. Okay, so this denominator will be 1 plus GH, and if this sign is positive, then it is called as the positive feedback, and then this overall transfer function will be equal to, if this sign is positive, then it is called as the positive feedback, and then this overall transfer function will be 1 G upon 1 minus ZH. So if it is positive, this sign will be negative. If it is negative, then this sign will be positive. Okay, then actuating error signal ratio. So E by R. So if you take this E by R, then this E by R will be equal to 1 upon 1 plus 1 upon 1 plus or minus GH. So this again, this will be plus when this is negative feedback, and this will be minus when there is a positive feedback, right? And then see, all those things can be manipulated from all these equations, this equation. Then B by R is called as the primary feedback ratio, which is equal to GH upon 1 upon 1 plus G into H. So this form of the feedback is called as the canonical form of the feedback control system. And the overall transfer function of this canonical form of feedback system is given by Cs upon Rs equal to G upon 1 plus Gs Hs. If it is negative feedback, and if it is positive feedback, then this will be Gs upon 1 minus Gs Hs. Right. So you have to keep in mind this formula, okay, of the transfer function of closed loop transfer function system, right? So the system is said to have a negative feedback if the sign at the summing junction is negative. So if the sign is negative, then it is called as a negative feedback, and system will be having the positive feedback if the sign is positive. So if this sign is positive, then it is called as the positive feedback. If this sign is negative, then it is called as the negative feedback, right? Now, see that the open loop transfer function is the product of this forward transfer function and then this feedback transfer function. So if you take this this one product, then it is called as the open loop transfer function. Now, what is the open loop transfer function of given system? So k into 0.1. So 0.1 k divided by 1 plus k into s plus 1. So that will be open loop transfer function. So this will be given by Bs upon Es equal to Gs into Hs. So this is Gs into this is Hs. Now, what is the feed forward transfer function? Feed forward transfer function is nothing but this one, Cs, this one. Cs upon Es. So this is Cs and this is Es. So Cs upon Es is nothing but this one. So this is Gs. So what is this Gs? Given in given system, it is k upon 1 plus k into s plus 1. So this is feed forward transfer function. This is feedback transfer function. Open loop transfer function means basically the product of this one. And closed loop transfer function is this G of s divided by 1 plus G of s into H of s. So that is nothing but the closed loop transfer function, or it is also called as the control ratio. So G of s 1 upon 1 plus G of s H of s. So since this is a negative feedback, so that's why this sign is positive. If it would have been positive, then this sign would have been negative. Then feedback ratio, which is nothing but Bs upon Rs. So this Bs upon Rs, if you manipulate this the entire equations, you will get Gs into Hs divided by 1 plus Gs Hs. So that is nothing but the feedback ratio. And error ratio is what? So that is nothing but this E of S is the error signal divided by reference signal. So E of S by R of S, which is given by 1 upon 1 plus G of S H of S, right? And then closed loop transfer function or control ratio is same. So C of S by R of S, here also C of S by R of S. And since it is a negative feedback, so this sign will be positive, G of S divided by 1 plus G of S H of S. Then what is the characteristic equation? Characteristic equation that you have to equate this one, the denominator of this closed loop transfer function equal to 0. So what is the closed loop transfer function denominator? 1 plus G of S H of S is equal to 0. So this is called as the characteristic equation. Okay. And the closed loop poles and zeros if k equal to 10. Now, if k is equal to 10, you can find out what is the closed loop this one poles and 0 by solving that equation and so on. Now, the characteristic equation C by R, as I said that this denominator of closed loop transfer function is called as the characteristic equation. So the denominator of C by R determines the characteristic equation of the system, which is usually to determine 1 plus G of S H of S equal to 0 or equivalent to this D G of plus or minus NG of H equal to 0, where DGS is nothing but the denominator and NGH is nothing but the numerator of GH. Right. So this is basically the characteristic equation. If you equate that one equal to 0, so from that we will know the characteristic of that system basically by finding the roots of that one. So that roots of characteristic equation is nothing but the poles, and from poles we can determine the stability of a control system. Now, what is by unity feedback system? So if the feedback element h of s is having value equal to 1, then okay, what will be the gain? So that will be equal to 1. So this system is considered as unity feedback system, right? So here the feedback element h of s will is having one value, then it is called as the unity feedback system. So unity feedback system is one in which the primary feedback b is identically equal to the controlled output h equal to 1 for a linear unity feedback system, right? So this is called as the unity feedback control system. Any feedback system with only linear time invariant system can be put into the form of unity feedback system by using transformation. Okay, and so basically here this figure and this figure is equivalent. What we have done, just basically we have converted this figure into the unity feedback system. But what we have done, so since we have shifted this block here, so we have to multiply this one by h. So here this is equivalent to this one. So what is the transfer function of this one? If it is negative feedback, so this will be g of s divided by 1 plus g of s h of s if it is negative feedback. So same thing will be there if you find the transfer function of this one. So that will be equal to g of h divided by 1 plus g of s h of s. So if you solve this one, right? So the main important thing is that this is the unity feedback system, and the given system you can convert into unity feedback system by arranging blocks like this way. Now we will see what are the different techniques or rules to reduce the complicated block diagram into a single block, or to find out the overall transfer function by using a block diagram reduction technique. So there are basically 8 to 10 different rules are there, and we'll see one by one all those rules, and then after that the problem can be taken on that one, right? So problem maybe we can take in the next lecture. Now see that first rule is that when two or more blocks are connected in cascade, like for example this is one block and this is another block which is connected in cascade, or it is also called as series. So if two or more blocks are connected in series or cascade, then overall these two blocks can be reduced into a single block having transfer function equal to the product of individual transfer function. Now, what is the transfer function of this block? That is equal to z1. What is the transfer function of this block? That is equal to z2. So, for example, mth block is also there whose transfer function is zn. Then we can reduce that one, all those blocks we can combine into a single block, and the overall transfer function will be just product of the individual transfer function. So z1 is the transfer function of this block, z2 is the transfer function of this block. If zn is the nth block here, so this will be g1 into g2 up to gn and so on. Means when two or more blocks are connected in cascade, then that can be reduced into a single block, and the transfer function of that single block will be just product of individual transfer function. So this is the first rule which is generally used for block diagram reduction. So that is nothing but combining blocks which are connected in cascade or series. Now, second rule, if you see, if two or more blocks are connected in parallel, like for example, this block Z1 is there, another block Z2 is there. Now, these two blocks are connected in parallel. Why they are connected? Why we are saying these two blocks are connected in parallel? See that this input is common to these blocks, and signal direction is same, and then output is just summing, right? So if this situation is there, then those blocks are connected. Then we can say that those blocks are connected in parallel. If suppose, for example, if this one, if the signal direction is in opposite direction, then those two blocks will not be in parallel. But if signal direction is in same direction, and then input is common and output is summing, then this is summing point. So this signal and this signal gets added here. So this symbol is called as the summing point, and this is the individual forward transfer function having gain equal to z1. This is another block having gain equal to z2. So for g1 and g2, this common signal is given, and output is basically combined here in a summing point. So what will be the output equivalent diagram? So we'd like to reduce these two blocks into a single block because we are studying block reduction technique. So rule says that if two or more blocks are connected in parallel, then those two blocks or more blocks can be represented with a single block, and then the transfer function of that single block will be just algebraic summation of that one. Here I have used the word algebraic summation, means if this is plus, fine. So this will be equal to z1 plus z2. But if this is z1 plus and this is minus, so this will be equal to z1 minus z2. That's why I said that it is algebraic summation of the blocks. Now these are the two blocks. Like for example, n blocks are connected in parallel. So what will be the transfer function? That will be equal to z1 plus z2 plus zn and so on, right? So we have studied two basically rules here. One is combining. If two blocks are connected in parallel series, then overall transfer function will be equal to the product of individual transfer function. And if two blocks or two or more blocks are connected in parallel, then overall transfer function will be the algebraic summation of this individual transfer function. So these are the two rules. The next rule is that, like, you would like to move, see, to make this block diagram, complicated block diagram, you have to do the arrangement so that some blocks will come in parallel, some blocks will come in cascade, and so on. So to make it parallel or series, okay, you sometimes you have to move this summing point ahead of the block, or if it is ahead, sometimes you have to move into the behind of the block. Now suppose for example you would like to move this block behind a block, so this is ahead here, and you would like to shift this block after this block or behind this block. So what is the rule? Now see that this signal is x and this signal is y, right? So this will be x plus y. So this will be x plus y multiplied by z. So output will be what? Z into x plus y. So when you are saying that it is equivalent, or your output should not be changed, right? Now see, this is x, and then if this is y, so you have to add one more block here so that your output will remain same. See that if it is x and this is y, so what will be this one? Y into z. What will be this one? X into z. And then this is your adding, so xz plus yz. So if you take the z common, so x plus y into z. What about this one? This will be x and this is y. So x minus y, because this minus sign, this is also minus sign. Okay, x minus y into z. So this will be also x minus y into z. So when you are shifting this summing point behind the block, then you have to add one more block, okay, and having transfer function equal to the individual transfer function of that one. So this is the rule for shifting the summing point behind the block, or okay, after the block, and so on. I hope that you have understood, because overall output should not change if you may change the arrangement. So what is the output here? If you are considering this as a x and this as a y, so this will be equal to x minus y. So x minus y gets multiplied with z. So this will be, overall output will be z into x minus y. Now if you are considering this as a x, this as a y, so xz, and this, what is that? Yz. So xz minus yg, z is common here, so x minus y into z. So this diagram and this diagram is equivalent. So what is the rule? If you are moving this summing point after a block, see that this summing point has been shifted here, but the arrangement you have to make is that you have to add one more block here in other path, so that overall transfer function will remain same. So this is the third rule of moving summing point after a block, right? Then the next one is, fourth rule is that moving a summing point ahead of the block. Like for example, this summing point is here and you would like to shift this one, right? Now suppose for example this is x signal and this is y signal. So what will be the output of this one? X into z. And what is the output of this one? Only y. So what will be the output of summing point? Xz minus y. So your output should be xz minus y. Now when you are shifting this one okay, ahead of the block. So what will happen if you keep this as a y instead of, okay, if you are not added this block, and if this is only y, so this will be x minus y into z, so which is not equivalent to this one, because this is xz minus y. And if you are just without adding this block, if you are having this y signal and this is x signal, so x minus y into z, so which will not be equivalent. So what you are, when it will be equivalent, then at that time basically you have to add one more block which is having transfer function equal to the reciprocal of this one. So what is that? That is equal to 1 by z. Now this is y. So y into 1 by z means y by z, and this is x. So x minus y by z multiplied by z, so that will be equal to xz minus y. So this is xz minus y, this is also xz minus y. So these two blocks are, or these two arrangements are same or equivalent. Means when you are shifting this summing point ahead of the block, you have to add one more block, and that transfer function will be equal to 1 by z. I hope that you have understood rule number 4. Right? Now, the rule number 5 is that, see, I said that in block diagram, there are important things like as a forward path, or feedback path, summing point, and take-up point. Now we have seen this one, summing point shifting, and ahead of the block and behind of the block. Now we'll see the moving take-up point, or it is also called as the pick-up point, behind the block. Like for example, this is the signal. Now suppose, for example, if I consider this as an x signal, what will be this signal? Again, this will be x only. All right. So what will be this signal? X. So what will the output? That will be equal to x into z. Right. Now, if I shift this summing take-up point here, what will happen? This is x, and what will the output? This will be xz. Now, if I take directly without adding this one, so this signal will be xz. But what was this one? This was only x. So our signal should not change. So to make this x, you have to add one more block, and that is equal to 1 by z here. So 1 by z is added here. So what will happen? X into z, and then x into g multiplied by 1 by z, that will be equal to x. So this signal and this signal will remain same, and overall transfer function will be equal to xz. Here also it is xz. So when you are moving a take-up point behind the block, you have to add one more block and having transfer function equal to 1 by z, right? Now, sixth rule is that, see, when take-off point is here, you would like to shift here. So at that time, you have to add one more block having transfer function equal to 1 by z. Now, suppose, for example, your take-off point is here and you'd like to shift this one at this position. So you have to make the arrangement. Like, for example, if this signal is x, so what will the output? Xz. So what will this signal? Xz. What will the output? Xz. Now, if I directly shift this one take-off point here without adding this g, what will be this signal? This is x. So without this block, this will be x. But what we want? We want xz. So we have to add one more block here having transfer function equal to z. So this signal will be xz. This is x, and then x multiplied by z will be equal to xz. So your output will be xz. Here also output is xz, and here this signal is xg. So by shifting this one, this will also become xg. So when you are moving a takeoff point behind the block, then you have to add one more block, and that transfer function of that block will be equal to xc, right? Then so these are the 6 different rules which are very, very important for reducing the complicated block diagram into a single or equivalent block diagram, or single diagram, single block. And from that, we can find out overall transfer function. So why we are doing all those things? To find out the overall transfer function of a complicated system by using block diagram reduction. So for block diagram reduction, there are 8 to 9 rules are there. And then already we have studied 6 different rules. The next one is the 7th rule, and that is basically that is your this one. seventh rule is eliminating the feedback loop, right? Suppose, for example, this is the one block having transfer function equal to z, and this is another block having transfer function equal to h. Now, these two blocks are in feedback. Why? Because your output is common and input is summing. See, in the case of parallel, input is common and output is summing. Here, in case of this one, your output is common and input is basically summing here, or the signal directions are opposite in direction. See that for z it is from left to right, and for h it is from right to left. So these two blocks are connected in parallel. This one feedback. Now what is the this one? If this sign is negative, then this is called as negative feedback. If this sign is positive, then it is called as the positive feedback. So if two blocks are connected in feedback loop, then that can be reduced into a single block having transfer function equal to z upon 1 plus or minus z of h. So this sign will be positive if this signal, okay, feedback is negative. Means if negative sign is there, then this will be g upon 1 plus gh. And if this is positive feedback, then this will be this sign will be negative, g upon 1 minus g of s h of s, right? So if two blocks are connected in loop, then that can be reduced into a single block, and that is equal to z upon 1 plus or minus g of s h of s, right? Now when the h of s is equal to 1, means it is a unity feedback, then what we have to put? Just you have to put the value of h equal to 1. Now if you put the value of h equal to 1, so this will be equal to z upon 1 plus or minus z, right? So this will be having plus sign if it is negative feedback, and this will be having minus sign if it is positive feedback. So for unity feedback, it will be g upon 1 plus or minus z, right? So these are very, very important 7 rules which we have studied in the 4-block diagram reduction technique. Now, swapping two neighboring summing points. So generally this rule is rarely used. All those 7 rules are mostly used for eliminating the feedback loop. But if there are two summing points which are basically neighboring, and then by swapping them, if it can be reduced into a simple one, then you have to swap that two summing points. So if summing points you have to swap, so see that if it is directly connected, then you can directly swap it. So see that this is a summing point A, and then this is a summing point B. Then see that this will be B and this will be A, since it is directly connected, and so on, right? So directly you can swap it. So here, see that to summarize this block diagram reduction techniques, see that first rule is that combining two blocks, or if two or more blocks are in cascade, then see that this signal will be x into p1. So xp1, this is given to input to p2. So y will be equal to p1 p2 into x. So your output will be equal to p1 p2 into x. Now x is input, y is output. So what will be the equivalent diagram, single? If you reduce these two blocks which are connected in series, that can be reduced into a single block, but the transfer function will be the product of individual transfer functions. So this is the first rule, right? The second rule is that if two or more blocks are connected in a parallel, if two or more blocks are connected in parallel, then you have to add these two blocks into a single block. Like for example, if this is x and then this is p1 and this is p2, see that input is common and output is added. So these two blocks are connected in parallel. So this will be what? P1 plus p2 into x. So y will be equal to p1 plus or minus. If it is plus or minus, this will be plus or minus p1 plus p2 plus or minus p2 into x. So just you have to do the algebraic summation, and then it can be reduced into a single block having transfer function equal to p1 plus or minus p2. So this is equivalent to this one, this is equivalent to this one, and so on. Another way is you can also do that is x into p2, and then you can have this unity, this one parallel system. So p1 by p2. So this is same also, right? Okay. Now eliminating the feedback loop. Okay, so if this loop, block and this another block is in feedback, see that output is common, but input is summing point, and the signal direction are opposite in each other. So here signal direction are same in parallel, in feedback they are opposite. So P1 and P2 are basically in a parallel, so now in feedback loop. So this can be reduced into a single block having transfer function equal to P1 divided by 1 minus plus or minus P1 P2. So this sign will be plus if negative feedback is there, this sign will be minus if positive feedback is there. So this can be reduced into a single block, right? Or in other way, this can be also done with a unity feedback system like this way, right? So remember this one. Then rearranging the summing point. Okay, like for example, original block diagram is this one, and then you would like to change this one. Suppose instead of this x, you would like to have the y here. So what is the aim? Aim should be that your z should not change here. What is the value of z here? See that this is w plus x, so this is w plus x, or w plus or minus x. And then what is this one? Plus or minus y. So z will be equal to w plus or minus x plus or minus y. So this is z. Now if you change this y, interchange x and y, so your output should not change. So see that what happens, w plus or minus y, so this is plus sign, and then x plus or minus, so this is same basically. Okay, this is equivalent to this original diagram, right? Now rearranging the summing point in this situation, right? So see that w, this is x, and this y. So this can be also, see what is the value of z? Z will be equal to w plus or minus x plus or minus y. So this can be also done with this arrangement, w plus or minus x, and see that what is the output of this one? X plus or minus y, right? Plus or minus x plus or minus y. So this is added with w, so that is equal to z. So this diagram and this diagram is equivalent, right? Then moving summing point ahead of the block. So what you have to do? Just you have to add one more block having transfer function equal to 1 by p, or that transfer function. So this block diagram and this block diagram is same, right? Now moving summing, okay, summing point behind the block, so or beyond the block, so like that way. So at that time just you have to add one more block with this another signal and having transfer function equal to p. So this diagram and this diagram is same, so your z should be same. See that what is the z here in original diagram? This is x plus or minus y, so which is x plus or minus y multiplied by p, so that is equal to z. So p into x plus or minus y. Now here also this is x plus xp plus yp, and then you are adding here, so xp plus or minus yp equal to z. So this z value and this z value is same, so this diagram and this diagram is same, right? And then moving the take-up point ahead of the block, so you'd like to shift this one. So this signal is what? So xp, this y is xp, and this is also y, and then this one. So if you like to shift here, so what will happen? If you directly take it will be x, but what you want this as a y, so which is equal to xp. So you have to add here one more block. So moving a take-up point ahead of the block, at that time you have to add one more block having transfer function equal to p, or forward path transfer function. So this diagram and this diagram is same. Then another rule, that is moving a take-up point beyond a block. See that you'd like to shift this one, exactly opposite case of this one. So what is this signal? This is x. So this signal, now after changing this one, this x signal should not change now. Otherwise, if you directly take this one, then this will be xp. What is this one? We want only x. So if it is xp, if you divide it by p, it will be only x then. So here 1 by p is added. So when you are shifting this takeoff point after a block, you have to add one more block in this path, and that transfer function will be equal to 1 by p. So your output y will not change, this will not change, this will remain same. So this and this diagram is equivalent to each other. Then moving a takeoff point ahead of the summing point. So see that this moving a takeoff point ahead of the summing point. Now see that for that you have to make the arrangements such that your y value should not change, x value should not change, and z value should not change. Okay, so for this you can make the arrangement like this. So this is x, this is z, okay, and then this is y, right? And then this is also added with this one, so your z will not change. Now what is the value of this one, z? So that is equal to x plus or minus y. So this also z should be x plus or minus y if you make the arrangement like this, right? Then moving a takeoff point beyond a summing point, so moving a takeoff point beyond a summing point here, then you have to make this kind of arrangement, right? So that no signal value will change by changing the arrangement. And so either, okay, we have to combine two blocks which are connected in series, which are the blocks which are connected in parallel, or the blocks which are connected in loop, or we have to shift the summing point ahead of the block, or we have to shift the summing point behind the block, or we have to shift the takeoff point ahead of the block, or we have to shift that takeoff point beyond the block, or moving a takeoff point ahead of the summing point, or beyond the summing point, and so on. So we have studied all those rules. Now we have to apply those rules to get the equivalent diagram and to find out the overall transfer function of a system if that system is complicated. So in today's lecture, just we have studied what are the different rules which are used for block diagram reduction. So when you are combining basically, okay, reducing the complicated block diagram into a single block, or you'd like to find out the overall transfer function, then there are certain basically procedures which you have to follow. So how you are going to proceed it? So first thing is that you have to look, first thing is that if complicated block diagram is given, you have to look that are there any two blocks which are connected in cascade. So if two blocks are connected in cascade, combine into one. So that is, you have to apply first rule immediately, right? If that two blocks are not connected in cascade, then see that if two blocks are connected in parallel, okay, then add it algebraically. If cascade is not there, parallel is not there, then what you have to do, you have to see whether two blocks are in loop. If they are in loop, reduce into a single block diagram. So that is your step 3. And then after that, if nothing is there, and you'd like to reduce into a simple or single block, then you have to change the takeoff point position either ahead or beyond, or summing point either ahead or beyond. So you have to repeat all those rules and simplify that block diagram into a single block diagram. But in the beginning, what you have to do, you have to look for the cascade blocks, then you have to look for the parallel blocks, then you have to look for the loops, then takeoff point shifting either ahead or beyond, then summing point shifting either ahead or beyond, and so on. And then, or interchanging of summing point, or okay, shifting takeoff point beyond the summing point, or vice versa. So like that way, you have to apply the rules, and then you have to reduce the block diagram into a complicated block diagram into a single block having transfer function. Okay, and then that will give the overall transfer function. So that's all from today's lecture. So in today's lecture, we have studied the block diagram reduction techniques, which are there are different 12 rules are there. So that is what we have studied. In tomorrow's lecture, we will study or we'll take some problems on that one, how to reduce the complicated block diagram into a single block, and how to find out the overall transfer function by using block diagram reduction techniques. So maybe in next lecture, we are going to study. So we'll stop here. If you have any questions, I'll be happy to answer all those questions to you. So over to you.